In this video, I'm going to talk about how to draw displaced shapes for structures if you know nothing else except for the shape of the structure and what approximate kinds of loads are on them. There are a few rules that we need to follow if we want to try to draw these kind of displaced shapes, and they're shown here. One is fixed ends remain fixed, so wherever you have a fixed structural end, if it looks something like this, and this is 90 degrees, then whenever this is trying to bend, the end always remains 90 degrees. Then you have 90 degree bends stay at 90 degrees, so that's when you have a bend in a structure. So you have a structure like this and it has a 90 degree bend, and you want to turn that over. Okay, this angle always has to remain 90 degrees. Okay, then no axial deformation, so we're just assuming that there is no axial deformation in any of the members, so they can't elongate or compress. Then we have compatible corner displacement, so let's talk about that. Number 4. Okay, so there are only two ways for a corner to bend. And they look like this, so let's see. Okay, so we have a corner. Okay, and we apply, this is an opening moment. Okay, so the corner is going to look like this. Open, open. This stays 90 degrees, and this is the way that the corner bends. Alternately, we could have a closing moment. So we have a corner that looks like this. We have moments like this. And our closing moment looks something like this. Okay, so again, the corner remains 90, and this moment around the corner has to remain compatible. So we can either have it both opening or both closing. We cannot have this situation. Okay, no, because here we have tension on the outside and tension on the inside. But these tension forces are not compatible around the corner, so there's no way that this can actually exist unless there's actually a point moment that's twisting this corner, which is very rare. So in general, we can say that this is not possible. Or this is also not possible, with tension on the inside and tension on the outside. Around a corner, the moment has to remain on the same side, so the tension has to remain on the same side like this. So again, this is only possible for an applied point moment. And that would be something that looks like this. Okay, then we could get this. If these ends are restrained somewhere, say this is restrained, like this, then we could bend it like this. Okay, another interesting point to make is how moment arrows work. Okay, if we have a beam that looks like this, and we bend that beam, okay, concave down for example, okay, then the moment arrows have to look like this. Right? So you can imagine grabbing this beam and turning it in the direction of the arrow. So you're twisting the ends in the direction of those arrows. The arrows always go from the tension side of the beam to the compression side. Okay, so obviously this side is in tension on this beam, and this side is in compression. So those arrows are always pointing towards the compression side when you have a moment. Okay, and the last point up here is to think about inflection points. So what does an inflection point mean? That's number 5. Okay, if we have a beam that's deforming in a shape that looks kind of like this. Okay, we have some sort of smooth contour. Here we have the beam deflecting in one way, and here we have the beam deflecting another way. So here we have a concave down situation, and here we have a concave up situation. Okay, and how that beam bends is related directly to what the moment is in that beam. So for concave down, like this is what we would call a negative moment. And for concave up, this is what we would call a positive moment. And we'd see that the moment diagram for this looks something like this. We have a negative moment here, we have a positive moment here. Okay, so this is as if we're giving it a twist like this, and a twist like this. Okay, and then where the positive moment, where the negative moment changes to a positive moment, that's where we have inflection point. And at that inflection point, it's the transition between the concave down and the concave up. And at that location, so that's where the second derivative is equal to 0, and the moment is equal to 0. So if we can draw a deflected shape and see where those inflection points exist, then we also know where the 0 moment points exist, and that'll help us in drawing a sample moment diagram. Okay. So let's look at some examples. We'll start with a very simple one. Okay, so we have a cantilever beam, and we put a load on the end. What happens? Let's draw it in blue. Okay, so here's our fixity. Okay, and our beam used to look like this. So we know that since this is a fixed end, we have to have 0 slope at that end. So it's going to look like that. And we know that this point is going to deflect downwards because of the load. Now, we're going to assume that the length of this doesn't change, so we're going to assume that this location stays on the horizontal axis, and we're just going to get the beam is just going to bend down like this. Okay, we assume that this length stays the same, constant, because we ignore the axial deformation of that beam. Okay, so that's a pretty easy one. Let's look at a harder one. Say we have what we call a portal frame, okay, which is just kind of 2 columns and a beam that connects them, all rigidly connected, and we put a force over here. Okay, well, we can draw right away. We know that the fixed ends are going to remain fixed. So let's draw this. Okay, we know we're going to have a fixed end here, and we know we're going to have a fixed end here, and these remain 90. Now we know that these 2 points are going to deflect to the right. So we can draw them a little bit to the right at the same height. Okay. We also know that those are going to rotate a little bit. Okay, because we push this beam over, we expect that these are going to rotate a little bit like this. Okay. So now we have to figure out whether these are going to be opening moments or closing moments, referring back to this here. So we know that these corners can either look like this, or they can look like this. Okay, so if we're looking at this one is moving to the right, so it's pulling away from this column. So this one is going to kind of want to open up, right? It's going to want to open up because it's the end of this column is being pulled by the reaction force. And with this one, we're going to assume that it kind of closes, right? So we can start to get an idea of what this is going to look like. So we're just assuming open versus close. Open versus close. And we can see that this drawing, as we've drawn it, doesn't really work. So let's try to draw it again, using the same assumption, and see if we can get the ends to match up. So if we wanted all these ends to match up, what would it look like? Okay, because we know that these beams have to be continuous. There's no hinges. So we have a vertical here, we have our other vertical here. Okay, and then let's kind of reduce the twist a little bit. And we have something that looks like this, closing, and then over here we have something that looks like this, opening. Okay. Maybe I gotta make them twist a little bit more. So this is kind of a step-by-step process. So this is opening like this, maybe, and then like that. So this is a closing one. Okay. This one over here is opening, so that means that it would have to bend back to get to the support, same as this one. Now this one is opening. So I have to get these two to match together. So I'm going to twist that. I'm going to twist this one a little bit. So instead of it being vertical like I've drawn it, have it go on an angle a little bit. It's an angle like this. This is an opening moment, which turns into a closing moment. So we can join those two together. Okay, so this remains 90. This is tension here, so that's good, and tension here, so that's good. And this is tension on the outside, which is good, and tension on the outside here. Okay, and so now where are our inflection points? So let's draw some inflection points in here. Okay, so we have tension here, tension here. So we know that this transitions from tension on one side to tension on the other side, so we have an inflection point in here. The same thing happens here, although I think that we can clean this up a little bit. Let's clean up the shape a little bit. There we go. So we have an inflection point over here, and then we have one in the middle up here. Okay, and then using those, we can try to draw an approximate moment diagram for what this situation would look like. So I'll just draw our frame. And let's draw the moment. Okay, we're drawing moment on compression side. So it's going to look something. Here, I'll start by putting, okay, so we're going to have a maximum moment here. Oops. We're going to have some sort of maximum moment here on the compression side. Then we're going to have 0 moment at the point of inflection. Then we're going to have another moment here. And then these have to vary to get to the 0, and there's no shear forces. You know, there's no forces being applied in between them, so we're going to assume that this is a linear change. We have the same thing happening on this column here, and 0 in the middle, so we can draw linear change. And then up top, we have compression on the outside, so we have that here. We have 0 in the middle, and then here we have compression on the inside, so it's down. And then we can draw this. Okay, and then we can see from this moment diagram that our moments are compatible around the corner, right? They can't change and they have to be on the same side. So this is the same moment here as it is here, and it's in compression on the same side of the angle on both. And then we have the same situation here, except now the compression's on the inside. Okay, so I'm just going to draw tension on the convex side. Okay, this is the convex side. Okay, so if we want to restate rule 4 about the compatibility of the moments around the corners, we can say that you must have the same moment and sign of the moment around a corner. And that's what that looks like. Okay, let's look at another example. Okay, say we have a situation that looks like this. Okay. We're still going to look at something that approximates a portal frame. Oops. But what it is kind of a portal frame with two overhangs that looks like this. And then we have a load that pushes down in the middle. So let's take a first crack at drawing what the deflected shape of this situation would be. Okay, so let's just kind of draw the undeflected shape first so that we know what we're looking at. I'll use a different color for the front. Okay, so now we know that this beam, this top beam, is going to bend down. So what if we assume that it's going to bend down like this? Okay, that seems like a reasonable assumption. We know that the fixed ends remain at 90. And so now if we wanted to join this, you know, this twists out. So this is going to have to kind of come back like this. Right, so it's going to have to come back like this to meet the fixed end. But, okay, so that remains 90. But we have a suspicious situation here, okay, because we have tension on the outside here, but tension on the inside here. So this corner is not compatible, right? Because we have an opening on one side and a closing moment on the other side, and there's no point moment here. So this is an incompatible corner. Okay, so we got to take another crack at this then and see if we can do a better job. Okay, so let's draw kind of approximate shape before the load first. Okay, here, let's draw it in red this time. Okay, so this time let's start with the corners. Now I think that it makes sense, it's reasonable that this should be closing, right? Because this has to come back to 90. So that this is closing makes sense. So let's draw that on the other side too. Because we have to end up back here. And this definitely has to twist out somehow, right? So that means that this corner here has to also be closing. Okay, for that to be compatible. And then to join these in the middle, we can draw something that looks like this. Okay, and then this goes straight out the end because there's no load on that. Okay, so now we have fixed ends are correct. These corners are still 90. But now we have a better compatibility situation at the corner where we have tension on the outside on both sides. Okay, so this is a much better approximation of the deflected shape. So now if we want to draw our inflection points, we have one that's right here, we have another one that's over here, and now we have a transition here. Tension on the outside, tension on the inside, tension on the outside. And now using this deflected shape, I can go ahead and try to draw what the approximate moment is going to look like for this shape. Just draw the structure first. Okay. So let's draw the moments. Okay, so here we have tension outside, tension inside here. Okay, so compression here is on the outside, so I'm going to draw compression. Okay, same on the other side. Then when we get to the top, compression's on the inside, and we have the 0 moment location from our inflection point at the middle of those columns. So we know that the column's moment is going to look something like this. We don't really know where this point of inflection is, but we know that it has to exist somewhere on the height of this column. And then here we have compression on the inside. Okay, so that makes sense because our corner has to be compatible. Then we have an inflection point here and here. And then at the top we have compression on the outside, so we're going to have something up here. So what this is going to look like, something like this. So if we want to fill in the, here's the beam moment diagram, and then the column moment diagram is this one here. Sometimes it's nice to just fill them in a little bit to see which one is which. Okay, and that makes sense, drawn according to the inflection points. Okay, let's see if we can look at a couple more while we're at it. Okay, so here's another example. Now we have a propped cantilever. Okay, with a load in the middle like this. Okay, now let's draw, that's what our undeformed shape looks like. Okay, we know that it has to be 90 degrees here at the fixed end. Has to remain like that. And then we know that it's going to meet up with this, although the slope of this beam can change. And we know this is going to deflect downwards like this, and then come back up. That's probably a little bit exaggerated. And then we find the inflection point, which is about here. And here this bending is always concave up, so there's no more inflection points. So here we have concave up, and here we have concave down. Okay, we have tension on the outside here, tension on the bottom here. Now if we want to draw the moment diagram, okay, we know that there is a compression moment. We know that there's a moment here with compression on the bottom, so we have concave down, so that's a negative moment. And then here we have concave up, so at the inflection point we have 0. At the end we have 0 because of the pin, and then we have concave up in between here. And so it's going to come up like this for sure. And then it's going to look something like this. And actually this is the point. This here is the point where the load is applied. Okay, and that comes, knowing that this looks triangular like this comes from a little bit of experience. Okay, but you can easily work this out for yourself as well, using some example numbers. And one last example, let's look at a 2-story moment frame. Okay, with 2 loads like this. And I'll show you what this one looks like. Okay, let's draw the undeformed shape as a reference. Okay, so we know we're going to move across here. We know we're going to move across here. This one is going to be pushed even further. These points. We know that this is 90 degrees here. 90 degrees. So this is going to rotate and go like this, and this is going to rotate like this. Okay. So this beam is going to have a deflected shape that looks like this. This one is going to be something like this with, and now this is an opening moment, so this has to come out and back, right? This is a closing moment, so it also has to come out and back like this. On this side, we have a closing moment, so it should come like this. I should draw this again. So this one is definitely opening, right? This is 90, so it's opening and then coming out and then back. And this one is the same, opening, coming out, closing, sorry, coming out and back. And let's draw some inflection points. Okay, so there's an inflection point here, here, here. There's one here, and this one is a little tricky. Let's try to redraw it a little bit. So it looks like this. Okay, and that's a little bit of a trickier one. But if we look at the moment diagram now, we can draw it like this. So we have compression here, so we're going to have something that looks like this. Same on the other side. Same for this. Okay, and then if we look at the beams, right, this has to be compatible, so this has to go down and that has to go up, so we have something that looks like this, and then we get the same kind of situation for this beam like this. And we have 0 moments at all of the inflection point locations. So that's a quick explanation of how to draw some displaced shapes. Really you need to get a bit of a feeling for it. One of the most important things to take out of this is that not only can you go forward in the way that we're doing and start at the displaced shape and try to estimate the moment, but it's actually easier to start at the moment diagram and go backwards and determine the displaced shape based on the moments, because these moments dictate whether it's concave up or concave down. Points of 0 moment give the points of inflection, and the other rules still count, like the fixed ends and the corners having 90 degrees, and then that way you can calculate the displaced shapes based on the moment diagrams. And that's what generally you'd be expected to do when you do a bending moment diagram question. But good news is that that is easier than this process. Anyway, good luck, and thanks.